Still hasn't opened now. Should you try again? See, when I searched MATLAB, MATLAB didn't come up. Activate MATLAB did come out. And deactivate MATLAB. Whatever. What the fuck? No, it hasn't come up yet. See, it's still initializing. There's that engineering license.
All the stuff I've heard is a bit overwhelming. So many different options and combinations.
Based on what he thought of. Got what he thought of? Alright, I think I'm going to start this thing. Sound good?
Did you start it? Or you
He started the recording, so whenever I actually start is fine. Okay, welcome to the Advanced MATLAB Programming Workshop, sponsored by the Center for Interdisciplinary Research and Consulting. My name is John, and today we're going to introduce some of the more advanced features of MATLAB and programming in MATLAB. If you're trying to use the full potential of this platform, these kind of things are really important. So we'll look first at logical subscripting. That's efficient and elegant. Then we'll talk about pre-allocation in terms of optimizing your MATLAB files, and we'll discuss vectorization of code as well for optimization as in the same context, and we'll talk about MATLAB structs and cell arrays for defining composite data structures. So let's begin. So you'll see on your packet on page 3 there, we'll start with our logical subscripting. When we type something like x equals 5, we're assigning the value 5 to the variable x. When we type something that looks like x equals equals, so that's two equal signs there, 5, we're asking the question, does the item x logically equivalent to the item 5? A 1 is a value true for that logical statement. A 0 is a value false. So if we typed x equals 3, which we know x does not equal 3, logically the logical value is false or 0. On the next page then, we define a vector. 4, 2, 0, negative 2. We'll assign it again to x. And we'll assign a vector y, which is 1, 2, 3, 4. If we logically ask, is x equivalent to y, it will check at each component of that vector if the values are logically equivalent. So the first value, 4 and 1, are not, but the second value, 2 and 2, are. So we see a 0, then a 1 in the logical equivalence vector. If we ask a question like x greater than y, we can still get logical values of true or false. Places where the x vector has corresponding value greater than that of the y vector is only the first position. 4 is greater than 1, but 2 is not greater than 2, 0 is not greater than 3, and negative 2 is not greater than 4. Another example would be to assess where x is less than or equal to y. Of course, that would be the last three components of the vector. So this is element-wise comparison. We can also compare a vector matrix by a single scalar, and we're going to do that here. So let's do x equals to -5 to 5, walking by 1s using our colon operator. There's our output for that command. And let's assign a value I to a logical output where x is greater than or equal to 0. So then the vector I identifies which places in that vector the x vector contains values greater than or equal to 0. So the I vector is a vector of logicals, either 0 or 1s. An identification vector, if you will. We're talking about a matrix here. Let's use one of our classic matrices, our magic matrix of size 4 by 4. Of course, it looks like that. And if we ask when is A greater than or equal to 10, for example, we see that the logical result is the place where each component is assessed as greater than or equal to 10 or not. 1s for true, 0s for false. Great. Now in section 2.2 we further discuss logical subscripting. We're turning to the vector x here. If we look at the case where our identification vector I is given by x greater than or equal to 0, our I is 0 in the first 5 entries and 1 in the following 6. If I assign P equal to x evaluated at I, the result is 0, 1, 2, 3, 4, 5. Notice that's the last 6 entries in the vector x. So I picked up the places where this logical condition was actually true. Any questions? Now let's look at an example here, the first of 3, where we look at a piecewise defined function using logical subscripting. Let me give myself a few extra spaces there, and let's say function y equals to f of x. So I'm defining the function all in hand. I'll type Shift-Enter to not return the command immediately, but rather type a few extra lines. And we'll make this y in value the size of x full of zeros. We'll use an identification here of -1, checking against the values of x, see if x is greater than or equal to those. Using our logical connective AND, x is less than or equal to 1. So pick up all of those places in this. We're definitely get rid of that extra parentheses. And finally, we'll pick up y at these places I, which is equal to negative I of x minus 1 dot times, so component-wise, multiplication of the values within the vector exactly in this way. And I made a typo. Let's see if we can find it. Guess we want to do this in a file.
I can't see anything because if I use
Yeah, just getting ahead of myself here, we could probably write that a little bit easier here in a file name. But I'll just copy these lines of code into a new function. And we'll save this guy as f.m. So we've written a function that tells us f of x equals to negative x minus 1 times x plus 1 if x is between negative 1 and 1. The value of the function will be 0 in any other case. So if we call the function f at negative 1, the value is 0 because negative 1 is 0 times negative 2 there, times negative 1 in the top case. What if we do f of 0? Well, since it's between negative 1 and 1, we'll have negative 1 times negative 1 should be 1. But if we do f of negative 3, or f of anything that's not between negative 1 and 1, the answer will be 0. There are other ways that we could, of course, write this function, but this is a pretty efficient way to do so. Now we want to do an example where we plot a curve so that portions of the plot may be emphasized, maybe by a choice of the line style or different colors. And we'll look at just a simple plot of the sine function in our case here. So we could do this in a script, but I think this one would be fine, just doing it at the command prompt here. If x is equal to, let's set it to be our domain here, 0 to 2 pi. And we define y equal to the sine of x. Let's make our first identification vector when x is less than or equal to pi, and our second identification vector when x is greater than pi, strictly greater than. Then if we plot the values x of I1 comma y of I1, right, the only places where those things are true, to do a different line style, we'll use a fill line there, and then in the second case we'll change the line style to be dotted. The second case here would be x and y, both of our second identifier I2. So we'll use a line style dashed line for that case. If we go ahead and hit enter on that command, we'll see our plot generated in figure 1. So while x is less than or equal to pi, we see that blue line, that's x of I1, y of I1, and while x is greater than pi, we see this dotted red line. That's when x is evaluated at the I2, the second identifier case. Clearly we could do as many cases as we wanted to. Logically there's no issue there. But certainly be careful when we're overlapping cases in something like this. Now let's say we're given a matrix for our third example with our logical subscripting, where the matrix contains some measurement data, and we know that these measurement data have some error tolerance. We want to know if any value in that matrix is below that tolerance level, and we want to zero them out so that we don't count them further in our analysis. So here's an example exactly how to do that. So since we don't actually have any measurement data, we'll use a random number, and we'll just take these guys to be small. So randomly generate a 5 by 5 matrix here, and we'll multiply that by 1/100th, giving us something that looks like this. Clearly, since we're using a random matrix, it will look different than the exact matrix in the tutorial printout at the bottom of page 6 there, so be careful and be aware of that. Now if we want to take A only at the places where A is less than or equal to our given tolerance. Let's say here we're dealing with 0.005, and we want to take those places where x is less than 0.005. We want to set those entries equal to 0. We can do it. Let's look at our matrix here. Okay, there are... I went and put an extra parentheses. There we go. So all of the places where A was less than or equal to 0.005 have now been replaced by a 0. So there we go. Three examples for doing logical subscripting there. Any questions? Okay. Let's go ahead then and talk about optimizing our M files. First, in terms of memory pre-allocation. So at this point, we're on page 7 of the handout. So when we're not pre-allocating some array in MATLAB, each time that it's enlarged, then the array is formally resized. Now, usually we allocate using something like a zeros function, but this is not the only option. In older versions of MATLAB, particular MATLAB 2011A, memory pre-allocation results in a less dramatic increase in efficiency than it did in more recent releases of MATLABs and older releases. But for a large enough problem, this is always a very smart thing to do. So let's see, we have some recurrence elation like the one here on page 7 where the first guy is equal to 0 and then the next guy is calculated based on 2 times the previous plus 3 for any guy in the sequence. So this recursive relation we can define via a couple functions. So let's go ahead and make a new function. Let's call him recur, RECUR1, for recursive relation number 1. And in that case, we'll allocate x as 0. So this is a pre-allocation based on the size of the problem of the variable x. So let me identify here with a comment that this is a pre-allocation. We'll compare against another function without the pre-allocation in a second. Go ahead and take a loop and write x of k equals to x k minus 1 times 2 plus 3. That's our recurrence relation here. And we'll type end. Perfect. That function is good. Save him as recur1. If I simply do a copy and a paste, and I take out this pre-allocation line and just make the first value of x 0, change my name to recur2, or non-pre-allocated recursive, then we have a new function, save that guy as recur2, and we can compare them. So the only difference in these two functions is the memory pre-allocation right before the loop. For small n, we're not going to see a noticeable difference. So if I do recur 1 of 10, answers right away. If we do recur 2 of 10, answer right away. Now, if we do a tick and a talk command, which we certainly should, as on page 8, we could assess much more clearly how long these things take. So this is a timing command now. TIC starts the clock. We run recur1 for a large n. Let's use one followed by 7 zeros. Once the computation is complete, we want to know to stop the clock and then tell us the time. So a tick-tock command in between the actual evaluation of the function. Off we go. So 0.21 seconds. Perfect. Now let's use that same exact command with recurve 2. So no pre-allocation in this case. .31933 seconds. So of course these are small values, but we're doing something quite simple here, and even these values for the size of this are fairly small, so this is an important thing to consider. I want to also reference you that table 1 there on top of page 8 gives some elementary and special vectors or matrices that are also useful in pre-allocation or array information for functions. The zeros array, we saw the ones array, and EYE for the identity matrix, the random matrix which we saw, size and length and end, about dimensions of the things. So take a look at that and consider those in your practice. Now let's talk about some more optimization, but vectorization. So looking now at section 4, unless there are any questions. All right, let's go ahead and move right along. So now we want to talk about vectorization, which is really the main technique used in optimizing code itself. So vectorization is carrying out the computations on data stored as vectors or matrices, of course, using linear algebra capabilities in MATLAB or the built-in functions to operate on those vectors. We know that in general loops are very slow, and instead of using loops we should use MATLAB's extensive matrix and vector capabilities whenever it's possible. So that of course is a result of the fact that MATLAB's matrix and vector capabilities are fully optimized. If you're interested in a more detailed guide on vectorization, we've listed a web address there. I'm going to go ahead and type it in, http mathworks.com support tech notes 1100.1109.html. So if I make my screen just a bit wider, it all fits on one. There's the link for more detailed guide on vectorization. Perfect. So our first example of vectorization is a piece of code that uses the idea of logical subscripting, in fact, and we're going to look here at if we're given two n by n matrices, A and B, and we want to form the matrix C, which is defined as the maximum of the corresponding entries of A or B, then we could look at the problem in this way. Pre-allocating our matrix C to be a matrix of size n by n filled with zeros. We haven't written in n yet. Let's do this in a script. Once we do the pre-allocation, we're going to write case 1 here, our loop, from I equals 1 to n. Then we want to loop from j equals 1 to n, since the matrix is n by n. Then we want to identify that this entry of the matrix C is given by the maximum of the entries A, I, j, and B, I, j. So the same corresponding entries. C, I, j is given by the maximum of A and B, I, j. End of the first 4, end of the second 4. there's our whole function. So let's call this max C. We could actually do this in the exact same way, being a bit more crafty. And the way we could be more crafty is, let me just do A equals to rand 5, B equals to rand 5. So they're both random matrices. If I set n equals to 5 here, that's the case I'm running inside of my max C, and I run it. Of course, I didn't actually print anything out, but I did get the result of C there. My claim is that we can actually get this result C in a better way. First, by writing C equal to B, then constructing I, an identifier where A is greater than B. See, once C is already set as B, all we need to know is where A is bigger than B. Then we would need to replace those guys in C by those corresponding guys in A. So we should see exactly the same C right there. We can almost fit, there we go, fit all of it on the screen. Perfect. So this is just a bit quicker of a way. It's both vectorized and logically subscripted. Very nice short implementation for that problem. Now let's look at another example that shows exactly the same idea of logical subscripting, but let's say now that we're given a 10,000 by 10,000 matrix, and we want to find out all of the entries that are less than 0. And if they're less than 0, we want to make them equal to 0. We could prepare this matrix doing something like A equals to rand of course, 10,000, and then making some of them, ensuring that some of them are negative by subtracting something like 0.5. I wouldn't leave off the semicolon in this case, and it will take MATLAB just a second to build such a matrix. So let's go ahead and write a little script to do this analysis, or solve this problem. Let's time our computation here, starting with defining a size, m comma n is the size of the matrix A, and then using our for loops for I equals 1 to m, and j equals 1 to n, so we'll allow A to be non-square in this particular implementation. And I really would like to give a little indentation there for proper structure. If A of I comma j is less than 0, we want to go ahead and make that entry equal to 0. And the if and the for, see, I accidentally typed enter rather than, this just isn't going well. Let me copy this and paste it there and finish this thing appropriately. Those are the two ends for the fors, and then we should end the tick with a talk. What a mess. This is going to take a little while. In an effort to observe that we can do this more efficiently, I'll kill that command with go to Control C, and I'll write this command: tick where a is less than 0 inside of a. We want to make it equal to 0. Logical subscripting. Hit it with a talk. The elapsed time there was less than a second. So we weren't going to wait all day for the other one to finish. It would have taken a good bit longer. Somewhere like 10 seconds. Does depend on the machine very much. You see in the tutorial here we've listed one as 8 seconds about and one as a 15th of a second, but here our machine is obviously a little slower since we were more like 0.6 seconds for the second case, and the first one just wasn't completing in reasonable time. So in this third example we'd like to explore now, we're going to look at if we have two vectors and we define their tensor product. Exactly as is stated at the bottom of page 9, standard tensor. Then we can write a function to do this. So I'll make a new function. Let me do this in the same way as we did one of our other examples. We did two functions. One with a pre-allocation and one without. Let's call the first one tensor 1 of a and b, where n is equal to the length of the vector a, and c is initialized as zeros of the size n, so it's n by n. And we have our for loop to do the work. Since it's n by n, we can make both of those go to n. Define the actual entries as a of I times b of j. That's our tensor product. And we have the end of the first 4, end of the second 4. Save that guy as tensor 1. Again, I'll just go ahead and copy this over to a new function, tensor 2. But we don't need really any of this stuff. So I'm going to go ahead and kill it all, actually. Let's say if we just write c equals to a colon times b colon dot apostrophe, that's going to give us a column times a row. See, this colon operator, or a of the colon, is converting any row or column into a column. So this a times is really a times this thing, which is the non-conjugate, or the real transpose here of b. If you want to know more about transpose, you can just type help transpose, or help C transpose if you're looking for conjugate transpose. In any case, we do need to save this implementation, and we want to save that guy as tensor 2. Save him right there. And we can test this with something like, what would be a good A? Well, a simple A would be 1 to 10,000. 10,000 is our favorite number for these. We don't want to get too big, but we want to define B as something like 10,000 walking back by ones all the way to 1. So the first one is 1, 2, 3, 4, 5, all the way to 10,000. The second one is 10,000, 9999, 9998, dot, dot, dot. Using our good old timing commands with tick and talk, we do tensor 1 of A and B. And I'm hoping this is going to be at less than 10 seconds. Four seconds. Tensor 2, much quicker. Not exactly much quicker in this particular case. So this machine we were able to beat it, but not by much. You see in our example here, when we ran that, it was more like a 4 to a 0.3 seconds on the same machine. I'm sure that you may also see different results on your machines there. We could use a larger size to see more drastic results potentially. But we are trying to move in a reasonable amount of time here, so trying to keep these examples to a short run time. Okay, example number 4. Moving right along. I know there's a lot in this tutorial and this session, but we're going to consider the operation now for a scalar product of two matrices that have real entries. So we have two implementations of this within the function test matrix dot, and the subfunction scalar for and scalar vect are those guys. Test matrix dot takes the input n, the size of those matrices, as an input parameter and generates random matrices A and B, then computes the wall clock time of both the vectorized and non-vectorized for comparison. So exactly what we've done here, really, in a similar setting now for a different problem. So if I write this function, so it's test matrix dot of n, where we have A is equal to a random matrix of size n, and B is equal to a random matrix of size n. We start our timing, and the first function we'd like to use is scalar product using a for loop, non-vectorized, and we can stop the time there. If you wanted to do a print statement that said something like this is the vectorized, this is the non-vectorized, that'd be a fine thing to do, and maybe I'll add that in a second. VEC for vector, product between those two, and then a talk. So let's go ahead and add those nice print statements. We do an fprintf, that'll display our value for n, since that's an integer. \I is an appropriate format for that guy. And we should say that it's going to be n, of course. We do another fprintf. We say for the non-vectorized version. I know that we haven't written the versions yet, but we're going to, in a sub-function here, just so we don't have to make too many documents for this example, just to show another way of doing things. We'll call that time t1. So what I need to do is up here, write t1 equals talk, and then we're going to call the other time t2 so that we can print them out. So let me just fix this to say vectorized, and since it's a floating point, t2. So there's our fprintf statement. So that's really all we want there, but now let's do a little sub-function action where we actually make the routine. So this is going to be a function that returns the value c, called scalar vec of a and b. The simple version here, of course, is c equals to the sum of a, using the colon operator again, now for a matrix, dot times b. It's the end of that function. We have a second function now that's going to return the same guy, but it's going to be a scalar for, or the non-vectorized. So using a loop. All of this is, of course, comparing loops versus vectorized, so we have to do a basic initialization. And we have a size that we need to read in. Don't need to return it. Then we need to do a for loop over the matrix 1 to n, and then again for j equals 1 to n. last of this function of course on page 12 of your tutorial. The contents of over the loop is c equal to c plus a of I comma j times b of I comma j. End of the j loop, end of the I loop. Function is complete. So let's save that guy as test matrix dot. If I do test matrix dot without an input, it says you didn't put all the inputs, but if we do input a value, which value should we do? Let's do our favorite value, of course, 10,000, and see what the results are. All right. Well then, we can always tell that MATLAB is still doing some things because it says right down here, busy. Didn't expect it to take this long. Certainly looks like this is taking much, much too long. I'm going to go ahead and kill this command, and what we're going to do is try a smaller value. We may have even frozen up this session. 10,000 was just too aggressive on this guy today. Well, interestingly enough. Are you here for the tutorial or are you here for class?
I'm here for class in 10 minutes.
10 minutes.
Is it cool if I take this tube?
Yeah, sure. I don't know why it's there, so be careful. Well, it looks like the machine is frozen. Classic mistake for running something too intensive. We're going to have to close this session out, and we're going to have to stop the tutorial here for today as there's a class coming in. We didn't get a chance to look at the sparse matrix examples, but I encourage you to do that, and we didn't get a chance to look at the composite data types. Maybe we'll take a look at those in another session. Thanks for coming, and I'll see you at the next one. Froze this thing up real good, Sam. Oh wait, look, it finished. It finished. There's the end. This time for real, it finished. All right, good. That's enough. I'll kill it myself. Yeah, that took way too long. I mean, command should have run much quicker, but this machine is very slow today.
Today?
Oh yeah, not necessarily today. In general, these machines are slow.
It should get better next semester.
Well, the instructor one is usually worse, I think, than the other ones, but it always seems to me like the instructor one is worse. If we had enough people running this thing, they all would have said, mine's finished. Well, mine's not, so we'll just sit here. What can you do?